Okay, so I guess for people, I guess we're live. So I guess for people who are new to the stream, hey, my name is Edbert. I coach people on how to land their dream software engineering job at Fang or other engineering companies, and I help them ace the coding interview. Right now, I guess the way to describe myself is I'm an ex-Apple senior engineer. I currently work at Uber as a Android engineer on the mobile foundations team. And right now we're just kind of like waiting until 8 p.m. until my client shows up. In the meantime, I'm just kind of looking at the holdings or the historical holdings of Monish Parbai. And basically the reason why I'm doing this is mostly just for like, what's it called? I'm really just looking at this to try and really analyze where he's making his investments. I think Monish Parbai is like really one of those investors that I really look up to because he started off as like, an engineer, started his own business, sold his own business, and then got into investing. And I think one of his really good philosophies that I personally like to follow is like being a shameless cloner. And so I'm trying to clone the cloner. Admittedly, it's a copy of a copy of a copy, but I mean, he's pretty good at this, having gone from like what? Getting like 26 to 30% returns year over year since 2000. I think that's pretty freaking phenomenal. So I think there's a lot that we can learn about his thinking, just kind of like looking at his holdings. And right now I'm just trying to reverse engineer like exactly what he held and why. Why did he reduce? Why did he sell out? And I guess I kind of want to go back to 2010, mostly because, we've been in a 10-year long exponential tech bull run. So I kind of want to, oh my fucking God, hold up. Let me actually just log into Guru Focus. Fuck this. All right. Let me go ahead and just move this tab over. In the meantime, I will put in Hacker News for you guys while I log in so you don't see my login credentials. All right, there we go. I think I'm logged in. I hope I am. Great. Great. Now I won't get the annoying pop-up. There we go. So I guess let's see. Let's see what he's holding here and why. He bought Berk B. He reduced it by 0.5 in 2016. So I'm guessing this was just exposure to Berkshire, but then also, oh wow, he dodged the Apple gain in order to. Okay, he reduced out of tech stocks about 2018. Okay, Micron Technology. So he got on the hype train before that. Sergey Growth Properties. Actually, I'm not too familiar with this. Let's see what this company does. It's probably some holdings, publicly traded stuff. It's a REIT. Okay, so I'm guessing that he understood the demand in housing. Yeah. So I think he's like, this is exposure to real estate. So I guess he just saw the demand for housing and got ahead of the curve. And I'm guessing that he read up on all the different properties that Seagate Growth Properties holds. Okay, so the company was formed to unlock the underlying value of high-quality retail real estate acquired from Sears. Ooh. Yeah. So if in case you don't know, Monish actually held Sears for a while back in like 2010, 2011. And the reason why, and it's a really interesting story. I need to find the clip again. But basically, he held Sears because he predicted that the book value was like 2 or 3 times what it was actually trading at. And then he had lunch with Charlie Munger. And then when he told Charlie Munger about his Sears holding, Charlie Munger apparently just shook his head and said, "Hey, you're wrong about this because it's very difficult to fire a bunch of people like all at once. It's gut-wrenchingly hard. So a company like Sears, even though your thesis might be correct, it would be a very long time to realize this gain." And so Monish actually just decided, you know what? It's not worth my time to actually get out of it, to actually wait for this to happen. So I'm guessing he bought this for 2 reasons. One was to get back into the Sears deal, and 2, given the timing of this in 2020, my guess is that he also combined that with the catalyst for the growth of real estate and the demand for real estate at that time. So since then, he's made like 40% off it, like something freaking insane. So he basically had two things going for it. I think that's just really the two things that he's really thought about. That's basically what I'm gonna guess is that when Monish makes these plays, I think that what he really does is like try to look for not just one but two factors that really go boom, you know, that make it drive it forward. And I'm thinking that this double down on Alibaba is pretty much the exact same thing. Is that he understands that even at the I think what he bought it at the 222 and then 206 price point. If I was him, I would think he would have doubled down again. Or I know Charlie Munger did after reading their filings, but I think he's looking at this again. There's no reason that Baba should be so depressed other than FUD in China, and I think he's already accounted for the premium of getting the money out. If you know anything about Alibaba, they actually own some piece, like some majority company stake in South Africa. The name escapes me, but essentially that company is a proxy for Alibaba itself, and essentially they're saying they're trading 75% to what Alibaba is worth, and that is basically the cost of getting your money out of South Africa. And I think he's basically applying the same principle in Alibaba, where it's like there's a 25% premium for trading on Alibaba. If you're buying through the what's it called, the VIE structure that they have. So my guess is that the price depression is just so good. And even though, despite that, there's a huge premium available to him, that he just sees it as just a really good opportunity. So my guess is that if he didn't add any more shares, it's because he already has a high portfolio. Yeah, he probably has a very high portfolio leveraged into Alibaba, and that he doesn't want any more. I think it's just like, I think that's really it. But I think he should double that. I think he would double down. I don't know why. I'm guessing that when the Q4 disclosures come out, I'm sure he doubled down. So maybe he just like thought that he was already holding too much. But I would say that at the cost basis, I want to see what his cost basis is. Fortunately, they don't actually say. Yeah, 21% is port is Alibaba actually. So let's look at the stock picks again. Yeah. So I guess he's holding it at basically a 210 cost basis, and the price right now is 162. So I think that he just doesn't want to add any more, just because he might be wrong, and there might be better opportunities elsewhere. Otherwise, I'm pretty sure he would have doubled down. Southwest Airlines, he sold out of it. Okay, cool. And he sold out of Surrogate Growth, and then bought back into it. Yeah, he unlocked it. They unlocked the value, and then real estate traded sideways for these 2 years, and he bought back in. Fair enough. Right now, I'm just seeing what else he might have held. Okay, so Goose's exponential bull run, 2014. Google. I'm guessing he predicted the spawner framework of Google back then. Bank of America sold out. Actually, is there a way to filter this by just the type of action? Holy shit. New buys. Yeah, let's look at the new buys. I think just filtering this out would be pretty good. Yeah. Holy shit. Look at this. He doesn't actually freaking buy a lot at all. These are all holding companies in the past freaking like 5 years. I mean, there's some tech companies in here like Micron and Google, but like these are all holding companies. Why? Why holding companies? What the heck is this shit? POSCO. I don't even know what POSCO does. Hold up. What's this one? PKX. POSCO steel prices and chemical business. So this is like some more infrastructure stock. Why the? Oh, it's a Korean manufacturing. Okay, I don't know shit about this one. Okay, it's Korean manufacturing. I can't really speak to this. So it's kind of weird. So I'm guessing, yeah, he's fishing outside the U.S. right now, but in the past he bought banking stocks. This is all-time low for banking. So this Citigroup, sure. Terex, what's Terex? American manufacturing, so for various industries. Okay, so he's investing in a lot of infrastructure stocks. So let's actually see what the So there's a lot of debt when he bought it. 2011, 1231. So he would have had to see probably back in 2009. So then he sees that there was a lot of debt, not much cash. He saw that, I'm guessing that he saw that it was growing. Was it? Was he? No. He saw like the cash growth was probably like middling, like on the verge of breaking out, and like the debt was low, was pretty high. The debt was going up. Okay, operating. Let's see annual. Maybe no, this doesn't show me that. The Peter Lynch chart from 10 years. Yeah, so he bought around here. What the hell? Price to earning ratio. Okay, so the price to earning ratio has pretty much stayed flat. Okay, so which means that the market is pricing it efficiently. My question now is, what prompted him to buy this? I'd probably have to read the stock report myself, but so far there's nothing that tells me that this was a good buy. Heavy construction and machinery. I don't know. This one I can't read into unless I actually read the 10K. But I think the overall thing is that he buys a lot of infrastructure stock. Like things that... Yeah. I'm guessing like things that are infrastructure or can be treated like infrastructure, like banking or farm shits. Yeah. He's buying a lot of farm. Infrastructure partners, 2010. Yeah. I'm guessing that's a lot of his early plays as well. So I think I would need to read these 10Ks, but right now I'm not picking up much. It's kind of hard for me to say like why he would pick certain stocks. Chesapeake Energy Company. He bought this in 2012. Okay. I kind of want to read more into 10Ks for these, but right now I'm not really getting anything out of this. Alright, I guess in the meantime, let's actually bring on our... I think it's almost 8 p.m., so let's bring on our guest. Let's bring on him from last week.
Recording in progress.
Okay, yeah, let's see actually... I guess while we're doing this, I want to look at Warren Buffett's... Oh, did I misspell fucking Warren Buffett? Ah, there we go. Yeah, 2 T's. Stock picks. Let's see, action... Okay, a lot of infrastructure stock. What the hell is this? Oh shit. Yo, this is a sleeper, boys. AON. Man, I gotta get this on AON. Insurance company. He bought this in 2021. I'm very curious why he bought this. Holy shit. Oh, British. Yeah. I'm very curious like why he bought this. I feel like there's a lot to learn. He's finding opportunities. It's very obvious. Like even in the past year, he's finding a lot of opportunities. Oh, I wanted to invest in this one actually, but I fucked up. BBvie. Oh well. Yo, hello.
Yeah, Bert.
Hey, what's up?
Yeah, sorry about that. I think I don't know why, but my Chrome just like crashed on me like 5 minutes before this, so sorry. Yeah.
It's all good. How are you doing?
I'm doing good. How are you?
Doing all right. Yeah, catch me up on everything that you've been doing since the last time we talked.
Got you.
I'm looking at the notes right now.
Hmm.
I noticed that we talked about like be more comfortable with running through an idea. Don't be overly obsessed with the details. Try to solve the problem logically. How
Yeah.
did that work over the weekend?
I think let me pull up my interview diary real quick. Uh, just check that out real quick. Mm. Yeah, so I think like in terms of like not paying too much, I think the biggest thing I kind of was trying to target, I think over the weekend was just I have a habit of like just going into the details a lot.
Mm-hmm.
And so like once I got the idea and stuff like that, I think like I tested it and it like worked out well.
Mm-hmm.
And this is specifically for like the leak code
Yeah.
kind of situation for DFS. In
Mm-hmm.
fact, I was just trying to do one right now. Like the 'cause sometimes like I think overall like it's not getting too obsessed over detail is I think I hesitate to say that I'm there, but it's just like I can get the idea and then I'm just testing it. So I'm
Mm-hmm.
running through the idea at least like one time, and I'm
Mm-hmm.
not being too overly obsessed with the details, I guess, when it
Mm-hmm.
comes to I guess testing per se.
Mm-hmm.
And so like there was that one. I did like so that's for DFS, and then we also went over like the permutations and stuff like that.
Mm-hmm.
And with that one, I think I don't know if it was just because like I didn't understand permutations that well, but uh, yeah, that one took me a long time actually to like think about. But overall, though, I think like it was all right. But yeah,
Okay, how many problems did you do? These are all the problems, or did you do more?
I did all of the grokking ones for the subset, and then the EPI ones for the traversal.
Mm-hmm.
For the binary tree, I finished that one,
Mm-hmm.
and let me see. Yeah, and I did like two LeetCode DFS problems.
Cool. How do you feel about your DFS? Because I know you were really struggling with that.
Yeah, I think overall in DFS, like I kind of talked to like R,
Mm-hmm.
and he kind of broke it down in a way that was like actually kind of good. I think overall, I think um, I'm getting better at it and whatnot. Like
Mm-hmm.
it's, but I hesitate to say that I'm like completely solid on it. But I think I'm like doing better on it. Yeah.
Good. What I want you guys to do with each other is really break down these ideas into simple
Hmm.
concepts and really like both of you put in the work and then be able to help each other. And I think that this is like it's starting to work a little bit. Like if you're able to get over that DFS hurdle, that's good news, and that's kind of like what I
Yeah.
expected. But he's on vacation, so I kind of hope that you can, um, break down another topic for him as well. Maybe he's got some questions, and that you
Yeah.
can answer as well. It's a give and take relationship, and you're both helping each other.
Yeah.
Yeah.
No, I feel that, yeah.
Mhm.
But in terms of for DFS, I think like I'm comfortable enough to like move on to another topic. I think
Right.
most likely I'm going to like still keep doing problems at the
Hmm.
on the back and stuff like that.
Okay.
But yeah, so
If I literally asked you to do a recursion problem, you'd be able to nail it.
for recursion, I mean we can try, yeah. Yeah.
All right. I'm sensing some hesitation here, but let's look over some of the problems that you did. Tell me the
Okay.
three problems that you think you did. Give me two. Actually, give me one problem you think you did well on, and tell me one problem, and give me two problems that you felt you did really badly. Let's start with the good ones.
Okay, for sure. Let me go
I mean,
through.
I'm looking at the practice diary. Just tell me which row.
Okay. I think the ones I did well on, they're actually not. Oh, I guess perhaps count paths for some
Ah,
on row 17.
okay. Okay, let me open that up.
Because yeah, that was one where it
I
was
need a
like,
request
oh, like good
access.
hustle, yeah.
Requesting access.
Okay.
Yeah, for these documents, just in the future, you could just make it so that way I can edit or whatever. So
Okay.
that way I can look at it at the off time in case you need me to look at something.
Sure.
Okay, let me know when it's been added.
Sounds good. Right.
Okay. Let's see. Given a binary tree and a number s, find all paths in the tree such that the sum of all nodes values of the path equal to s. Please note that nodes can start or end at any node, but all paths must follow direction from child node. Okay, cool. So I see. So there's 7, 5, 1, 9. Okay, 2, and then 9, 3. Great. Let's see how you solve this. So DFS algorithm at each node, keep track of the current path, add node to the current path, calculate all subpaths ending at the node. If a subpath equals s, increment counter function, and then you recurse into the left path and right path. Okay. So you're calculating all subpaths. When you say calculating all subpaths, do you mean the sum of all the paths and all permutations?
Yeah, so yeah, exactly. So it'd be like every possible path that ends at that node. Starting from like the root, let's say. And then like, yeah.
So starting at the root. So then walk me through an example of this. Because it's to me, it's like, I get it, but I think I want to hear how you describe it. Because it's a little vague, but I want to hear what you said.
Yeah, for sure. Yeah. I think for this problem, it's like, it was always a problem that like caught me like off guard a little bit in terms of how to solve it. And I think the reason I said like good hustle is because like I wasn't trying to like overthink it really. I was just like, oh, like fuck it, like, you know, like this is I think what it's supposed to be and whatnot. So if we were to, let's just say, start with example 2, right? Shit, I have to read all the tests. Okay, but if we were to just start with like example 2, we would start with node like 12, right? And let me type this in. Yeah, we start with node 12.
And it says you took like an hour to do this problem.
Oh, it does?
Hour and 30. Oh, no, it's permutations. Never mind. Wait, is that right? No.
But yeah, our permutations took like an hour and 30. Honestly, for that one, it was, I think, I was just like reviewing and stuff like that. For this one, I didn't keep track of the time.
It's fine. Okay, just in the future try to, but yeah, keep going.
Okay. Yeah, so for this one, it was just basically like, you know, we're at node 12 and we have something called like current path, right? Let's say up here. And at node 12, essentially, we would add this to the current path. So current path is now going to be equal to like 12, right? And then we move on to, we calculate all the subpaths ending at the node. And if the subpaths equals to s, like we increment the counter. And we have something, let's say, like a counter, like a global counter, like up here.
Sure.
Like 0. And so we see the current path right now is just like, it only has one element in it. It's 12. And, you know, what we're trying to get right now is 11. So nothing really happens to the counter at this point. And going back to the code up here, the pseudocode, we go into a function called node.left. We pass in path. Now we have current path equal to 12, and the node is now, since it's left, it's going to be 7. And current path, we append that to it. Check. Yeah, add node to current path. 12, 7, and now we start calculating like all the sums that end here. So there's only like 2, or there's only one node before 7, so the sum is like 19, right? 19 does not equal to 11, so nothing happens there. And then we keep going, right? We do function node.left current path. And now we're going to be current path to 7, and now we're on node 4. Current path is going to be equal to 12, 7, 4. And so now it's like, you know, we calculate every path that ends at 4, starting with like 12, right? So 12 plus 7 plus 4 equals to like 23. Right?
I see what you're going for. Okay.
And then 7 plus 4 equals to like 11. So essentially, like, you know, this like looping through, this is like kind of going to be like a loop and stuff like that. So because it's 11 and we have this global counter, we can just like just do counter plus equals to 1.
Okay, I see. All right, I understand your algorithm now.
Yeah.
And was this the thing did you write the actual code for it?
To be honest, no, because like I felt, because after I kind of did this algorithm, I kind of looked at the what the solution was, and right before they actually had the actual code, I kind of looked at it and I was like, okay, this kind of matches up. So yeah.
What do you mean kind of?
Like, I'm pretty sure like the logic for this is correct when I was comparing it to the solution. Yeah.
I would bet that. How about this? Share your screen with me. Share everything in the solution. I'm gonna bet right now that what you're thinking is that I got the solution right, and so I'm gonna iterate through every single current path, right? Like, so for instance, you said you're gonna check 12 and 7, right? And then you can check 12, 7, 4, and then 7, 4. I'm gonna give you a chance. What do you think the inefficiency with what you just described might be?
Essentially the inefficiency is like I'm calculating multiple times.
You're iterating through the array multiple times. So I'm gonna give you a chance. Off the top of your head, what's the easiest way to fix this?
The easiest way to fix this would be, so if we don't want to be we can, instead of adding like 12 and 7, everything, like we can just like store those values somewhere else, I think.
Okay, and in more specifically,
so we want to store the values somewhere and we want to correlate it to this current path array. I think the easiest option would be like storing like the values as like the keys, and storing the keys as like the current path, like no values. So 7 is a key, 12 is a key. And
I'm gonna say it's not quite there. What I was gonna say is that, well, the inefficiency, if we walk through it logically, the inefficiency is that you're right. You're walking through the array over and over and over again, right? You're adding 12, 7, and then 7, 4, right? Effectively, what you're doing is actually adding every single path to 7 plus 4. You see where I'm going with this?
Wait, say that, Edbert, can you say that one more time?
You're effectively adding every single path to 7 plus 4.
Yeah.
And then, so instead, why don't you just pass in why don't you just pass it in from the previous node? That way, each time you're only adding 4.
But like, if I'm passing that in, wouldn't that like, because if I pass in the value like 12 plus 7, is that what you mean? Like the previous like sum from like whatever node it was on?
Yeah, you would. So here, what could happen is you could pass in 19, 7 into the function. That way, you're not like iterating through the array over and over and over again. I mean, effectively, you're still, and then by doing that, you actually eliminate the current path.
Okay.
Does that make sense?
Not entirely. Could you, I guess, like elaborate with like an example that has
Sure.
more
Yeah. So to me, and this is like, I've never even done this problem, but this is like what I'm looking at. So you right now at this node, right? Let's play off what you just did. 12 node 7, right? Like you said, you're calculating all sums that end at 7, right? So it'd be 12 plus 7, and then 7 itself, right? Because you know, in the node itself could easily be the sum, right? Yeah. But essentially, you're going to traverse that same path again when you recurse into node 4, right? So you have this 12 plus 7 and 7.
Mm-hmm.
And then you're adding 4 to it, right? And then also you're going to be testing 4 itself.
Oh, so you're saying like...
So then when you go into the next node, let's suppose that there's like a 6 here, or 6 here. Then you just end up passing in what? 19, or just say 23, 11, and 4.
Yeah.
Mm-hmm. You notice like how I didn't even have to do the problem. I just played off your example and just noticed, hey, wait a minute, you're adding all these inefficiencies. So my guess is that if you wrote the code exactly how you described it, LeetCode would time you out.
Yeah. Okay. Yeah.
So you see, like I like when you say you kind of got it. Let's see what the LeetCode actually says. Do you have access to that, or is it
Let
free?
me.
I hope it's not premium.
Well, this was actually a grokking one.
Oh, is it grokking? Okay,
yeah.
let's actually see grokking. I'll log into my grokking account.
Yeah. I think this is.
I think your algorithm is correct though. That's the thing. So, which section is this one under?
This one is under. I believe this is DFS actually.
Oh, DFS.
Yeah.
Okay, depth research. Paths.
Yeah, this is this would be DFS.
All paths for a sum. Okay, let's see. Oh, I just got your Discord message now.
Okay. I was like mad sweating. I was like, oh my god.
It's okay, don't worry. Okay. Yeah, I'm gonna pull up the solution up on screen right now. Let's see.
Okay.
So paths to sum. So they actually keep a list of integers, list of all paths. So actually, they do actually what you said. That's the funny thing. Wow, they actually do keep a list of the paths. And then if the current sum is equal, then add all. I assume that, yeah. So they make the assumption that there is no negative numbers in grokking. Okay, that's fine. And so I understand where this comes from. But yeah, if there, I think that you had the right idea. You just had a few things like pruning, increment counter, function left, function right. I think it's just gonna be your if statement that's gonna throw you off. But if let's assume grokking is absolutely correct, right? Then I think that no. They keep the current path, but they never calculate the path. Effectively, what they do is they just subtract off the sum. Wait, am I looking at the right one? Wait. All paths for a sum, right?
No, count paths for a sum.
Oh, sorry, I'm looking at the wrong one. Okay, sorry, my bad.
I think what they do is actually.
Let's see here. Count current path. Yeah, so they keep the current path. Current path list iterator. They copy the path and then they iterate. Let's find all the subpaths. Yeah. Yeah. So okay, so then current path gets added. Current path dot list iterator. Current path dot size. Sure. Path. Okay, so they return back the path count actually each time. Okay, fine. And then this loop here is the one I'm curious about. If path iterator has previous, they go back up and add the path sum. Let me see the pseudocode again.
For sure.
As we add a current new node to the current path, we should find the sum of all subpaths ending at the current node. If the sum of any subpath. Yeah, it's this subpath that's going to be the interesting part. Path sum. Plus path sum equals 0. So they are... Oh, they're iterating it through it.
Oh, they're doing it in reverse. Looks like.
Yeah, they are iterating it every single time. They're doing it in reverse. What the hell? Yeah. Yeah. So that makes sense. So actually, they are iterating through it. Let me explain something. I understand what they're doing here now. They're doing it slightly different than you, and I think this is actually a pretty big detail. That's kind of the thing. So for instance, instead of trying 11, instead of trying 11, 12, 7, 4, and then trying 7, 4. They just try 4 and then try that, and then 4, 7, and then 4, 7, 12, right? And that's just a process. That's just a consequence of them iterating backwards. So they're naturally going to like hit these, but they still kind of like run to the exact same issue actually. But it's a little bit cleaner than I think what you did. I definitely would have liked to see how you implemented. It's gonna come down to how you implemented the all the permutations of the current path. Actually,
Okay.
do you see how detailed I'm being? I think I want you to get that idea, like what could go wrong if you didn't write the actual code.
Okay.
So,
Yeah, I think this time around I was a bit more like careless because I was just like I like as long as it kind of passes like the test conditions or something, or as long as it passes like in my head or like when I write it out, then like yeah. But you're
it's
right.
like yeah, it's these little details that kill you. That's ultimately like once you get to a certain point, it's those details that will fuck you up. So I think it's just really important to acknowledge that what is right, what is wrong here. So
Okay.
I writing the pseudocode, it's like it's risky. It's once you understand the pattern, and then you need to also acknowledge what part of the implementation could fuck you. And to me, this is like, and like I already like instantly when you wrote the algorithm, I already knew, this repeated path adding is gonna fuck you on runtime.
Yeah, I guess the reason why I chose to show this is because like before like a problem like this, like I would think like, oh, like don't do this like kind of calculate all the subpaths ending on node.
Uh huh.
Um, but then when I looked at kind of like their version of the pseudocode, right, I was like, oh shit, never mind. Like they also do this. Like
Mm-hmm.
so I thought I was like, oh okay, like maybe I'm over like I shouldn't be overthinking that much, like, but
I
yeah.
mean, to be fair, this might also fuck memory because the trade-off is that instead of using log n for the path, you're using essentially what one, two, three, you're using n memory. Yeah, you're trading off log n memory for n memory because you're trying to keep all the possible permutations of the paths ending at that node. No, you have no, you still have log n because these are just sums. So it just improves your calculation a little bit, but you still end up doing actually
Yeah.
the same number of calculations. I take back what I said about the optimization. It actually doesn't end up being that much better.
Okay.
If you do it like the way they do it, it actually doesn't end up being that much better. So yeah, so like the key boils down to how you're going to actually execute the summations. But it's like you see how that's where my mind kind of went, like what can go wrong. I really want you to like think that way when you're evaluating yourself, and it will.
Okay.
The reason why it's because it'll help you really understand what to test for.
Okay.
So, like
Gotcha.
understand. So I'm gonna write that down for you. It's a little bit more abstract, but it's a key concept that will carry you through a lot of problems. Think about what in the impl will mess you up. So then I'm just gonna cite the count paths for a sum. Impl of iterating through a path. And I think that trick of iterating backwards in order to try and like not have to repeat your calculations over and over and over again is super useful actually. I would keep that in your toolbox. Just remember that little trick.
So I guess like if you can explain like why are they choosing to do it backwards actually?
Okay, so let me repeat it. So instead of like, let's suppose that we want all the numbers, we want all the paths that end at a particular node, right?
Mm-hmm.
So in our case, let's go back to 1274, right? So what I can do is I can just say, hey, I can write my loop as like for I equals 0, I till less than end, I plus plus or something like that. And then I would just like loop through entire array. So it would just be like sum plus equals I, element at I, and then if sum equals target, then counter plus plus. And then I would just say for j, let's just say, yeah, let's actually say sum equals j. J, and then loop through entire array, j equals to I, j less than end. You see, like this would be probably I think what you were thinking.
Yeah, loop through. Yeah, definitely.
Yeah.
I think yeah.
This is like what you're thinking, but like I said, you're gonna get fucked on iteration. So effectively what you just did is like 12 plus 7 plus 4, and then 7 plus 4, and then 4, right? But instead, why don't I just do it in backwards? Because then I'm going to test 4. Then I'm just going to add plus 7 to that. Then I'm going to add plus 12 to that. So instead of me iterating through it every single time, I'm just like I'm getting the exact same result, except I'm not like trying to repeat this 7 plus 4 calculation. Or this 4 calculation. Yeah. That's basically it. It's a very useful, I think it's a very useful trick. I think it's worth remembering.
Okay, yeah, I see. Because they're only doing like one time. Okay, yeah.
I think like remember Remember going backwards as a way to skip repeated calculations. I think this is a very good trick. I think K, not you, R got messed up by this on one of his other problems yesterday on stream. And he's like, oh, why didn't I just see the reverse or backwards? I think backwards iteration. And I think this is a good trick for you to remember going forward. Gotcha. I know we're spending a lot of time on like critiquing, but I'm really trying to tone your senses of like details.
No, I think that's fair because I kind of low key, like my ideas sometimes get like a little bit weird sometimes, I feel. So it's good to kind of have these like toolboxes just to kind of supplement that. So.
Yeah, so I'm being really nitpicky here. I'm really trying to fix these things, because these are gonna like once you get like the pattern down, and it's really these nitpicks on like understanding what details can kill you that is really gonna start mattering. And you're starting to reach that point. So let's see another. I want to see a problem that you felt like you struggled with, and I'll tell you why.
Okay, so this was actually like very like recently, and this is the flattened binary tree to linked list. I think it's actually not too difficult, but I looked at my solution was completely different from their solution, and this was kind of for the DFS one. So let me just share this with you.
Let me request. I'm gonna request access to this doc actually.
Oh, okay. Yeah. Is it on the Google? Okay.
All right. Let me know when.
Okay. All right.
Okay, cool. Okay, let's take a look. Given the root of a binary tree, flatten the list into a linked list. The linked list should use the same tree node class pointers where the right child pointer, blah blah blah. Okay. You did an example, right? Flatten the tree into a linked list. Did you copy paste an example in here or not?
Oh, no.
I just Google. I'm pretty sure I can Google the problem and find one.
Yeah, just let's see.
Okay, got it.
Okay.
Yep. Okay, so I'm looking at the example right now off of LeetCode. And so, okay, so you're given a tree, and then you want to make a pre-order traversal of the list. Okay, so if you do 1 to LVR? No. VLR traversal. Okay, VLR. Okay, yeah. So you want to do a flattened VLR traversal. Great. Okay. So do a pre-order traversal and store all the nodes in an array. Create an initial node tree before iterating. Iterate through the array and for each. Okay. Yes. Okay. So you're actually going to do the pre-order traversal, store that in an array, and then just like link everything link all the nodes that you've stored. Okay.
Yeah.
That's fine. I think that this is gonna be the naive solution. Why? What's inefficient here?
Well, it's inefficient, I think, because essentially like they're asking us to do this in place, right? And I think there's like a
that should be ahead. Like, what is inefficient about your solution right now? I know where you're heading. I want you to do step by step, just so we're not skipping steps, just for the sake of exercise.
Got you. I guess like quite honestly, like the inefficiency I see is just I am constructing like a tree node when it already kind of like exists.
A little bit simpler language, a little bit more specific. What exactly is wrong here?
I'm like creating like n nodes when n nodes already exist.
Yeah, you're basically using extra memory. Even though they're technically references, they're cheap, but it's extra memory that you could probably not use. On top of that, you are running through you're running on order 2n, one time to iterate, one time to link. This is what I want you to really do when talking about your inefficiencies. I want you to keep it as concise as possible. Okay.
I see.
Possible when talking about inefficiencies, i.e., what's the problem is this flattened binary tree to linked list. And I want you to like really think about like I am doing order 2n because as I am iter through the nodes twice. Yep. And then the other one, or it's like I'm using extra space unnecessarily. So because if you talk about things like this and you say it like that, then it makes it very easy. So, because now you're gonna say, oh well, what does it take for me not to iterate over the nodes twice, or what does it take for me to do things without extra space?
Okay. I
So
see.
and the way you described it was like, oh, is like a little bit too abstract. Keep it down to earth, man.
Okay, got you.
Yeah, I really want you to talk to yourself like this, because you keep it down to earth. It makes it easier for the interviewer to follow you as well.
Got you.
Okay.
Yeah.
All right.
So yeah, for
let's
this
go
one,
ahead.
like my solution, it was like accepted. I didn't think it was actually going to be accepted and whatnot, but because that's when Chrome crashed. So I literally thought my solution broke Chrome. No, I'm being dead ass. Like I was just like, dude, what the fuck, man? But
this is why I'm saying leak code is not consistent. It's like it should not accept. I would like not accept this answer.
yeah, but like it accepted it, and then I'm looking through all the solutions, and like they like I don't do any of them. And I guess like I don't know really how to describe like where I feel is other than I guess just the inefficiencies and stuff like that, because it comes down to like, okay, I'm looking at the runtime and I'm like, okay, O of 2n, that kind of is like O of n and whatnot, and then yeah, I am taking up like O of like n space and stuff. But like at the crux of it is just like my approach is just different than every one of these solutions.
Your approach, you came up with an naive solution. I'm gonna say you're fine. You just made it to step 1. The question is now, how do you get to step 2, which is solving those inefficiencies. So I'm gonna give you a chance here. Let's pick up where you left off. I want you to actually figure out how you go from this to a more optimal solution where you can do it in place. I mean, looking at this problem, I have a good idea of how to do it, so I can kind of like judge you. But yeah.
Okay.
Go ahead.
Yeah. But yeah, before all that, that's why I was like, okay, I feel more comfortable with DFS now because it was just like traversing the tree and whatnot, like using recursion.
But now I want you to improve upon this, because just simply throwing DFS at a problem or whatever is whatever. I want you to improve upon this.
Okay. So yeah, the naive solution is just kind of doing this the pre-order way, improving on it. I think like let me copy paste this example real fast. So right now we have essentially 2 inefficiencies. So the first one is like I'm traversing it like twice, right? And the second is like the space, actually. I think in terms of for space, something I could do is in terms of space, okay, how can I would point. I have these nodes, right? All I need to do is rearrange them in some order. And the left subtree is, it looks like the left subtree right now is less than the right subtree. So this is a binary tree. It's not the problem. Okay. And the left subtree values are less than the ones on the right subtree. Sorry, this is kind of a dumb question, but do binary trees have that property where it's like the left subtree has to be like less than or equal to like the right subtree, or like just less than the right subtree?
Yeah, it does. So are you sure you're working with? Although this looks like it's not even a proper binary tree. It's like it's a improper binary tree. I don't remember what it's called, but like it's just a tree. It's just a tree. Let's call it just a tree.
Oh, okay. Fuck. Okay. We have to move whatever's on the left-hand side to the right hand side, right? And how do we do that? Well, what if we just pointed everything that was on the left hand? So 1. 1, 2, 2, 3, then 3, 3. Oh, what if you just did the pre-order traversal, and at each node that you do the traversal with, you're just setting the left, whatever was previously on like the left to like the right hand side.
Okay. And then what are you returning?
We wouldn't be returning anything.
Okay.
So like the idea would just be like, let's say we're at like node 1, right? And we're doing like a pre-order traversal. Node 1 has node 1 has like 2 as is like left hand, right? And then so using pre-order, right, we would go into 2, and whatever was like, we would go all the way down until the well, let me just start with this relationship right here, 1 and 2, like 1 and 2. So if it was, once we go left, right, we see that it's 2, and let's say there was nothing like under 2, then we would just set 1's left child. We would store 2 as like just in the temporary, I guess, like, or we wouldn't even have to do anything really. We would just set like 1's right child to 2 and just point it there.
Okay.
That's like an initial idea right now. And so now like so now 1's kind of pointing at nothing, and then we have like 2 here. And I know there's like 5 and 6 to worry about right now, but like I'll worry about that like after I finish the left subtree. So
sure.
Now 2 has like 3 and okay. And then if we're still doing the pre-order traversal, we would go into 3 right now. And following that same kind of idea, we would set 3 to 2's right child. Now 2 has something in its right child right now. So what we could do is like, we could just set that to 3's right child as well.
Okay.
Moving that into it.
Okay.
So then it'd be 3. And 4.
Okay.
Right.
Okay. And then what do you do with this?
Yeah, and then so afterwards, you know, we would be going back up, like we would return back up to 1, because the pre-order traversal would look at the left subtree first. Yeah, 1, 2, 3, 4, and now we're in the right subtree. And okay.
It gets a little bit complicated. Even I had trouble doing this in my head, so I'm gonna say, do this. I want you to write out what you just did, step by step. I think it's a little bit hard to keep track of, and then I'm gonna show you something.
Okay. So, can I just use pseudocode?
Yeah. Like remember, like we talked about, like trying to use just plain English, right? I want you to do it plain English, like I'm a 5-year-old child. Okay.
Order traversal starting at each node. Take number left child is and set it as the right child. If the right child exists, take whatever the left child is set as the right child. The left child, if a right child exists. Okay, right child exists.
Pre-orders. Okay, at each node, take whatever child is left and set it as the right child. Oh, I see what. No, don't worry. Don't worry.
Right child exists. Yeah, I'm kind of blanking on like what to do with the right child. I'm thinking. Like,
I'm going to stop you right here because I know where you're heading. I'm gonna kill you. I'm gonna stop it. The reason why is because I'm gonna show you something interesting. What you're essentially, you want this to be a recursive problem. It boils down to recursion. Let's think about why. Because you're saying we want to be able to traverse this without using extra memory. We want to, and we want to traverse it once, which means we're forced to use that traversal, right? That traversal method that we have, right? The question now is, well, in that traversal, what do we want to pass in? What do we want to get out? And I'm going to write this down for you. Like, for every recursion, are we passing in? What are we getting out? Right? So in theory, the nice way to do this would be, hey, I'm going to pass in a node. Input, node, output would be the flattened list of that node, right?
Right.
So let's call that a recursion function. So if I had that, then let's say I'm at node 1, right?
Yeah.
What would be the nice way to like I'm at node 1, what would be the nice way to write this function? Suppose I gave you a recursive, something called function that would do that for you. What would be the algorithm at node 1 that you would ideally like to have?
Yeah, so if I pass them like node 1, then the algorithm would just be like, okay, take like whatever the.
I want you to write out where I put my cursor. I just so that you're not doing it in your head.
The subtrees rearrange in pre-order fashion.
Okay.
And then like all the rearranged nodes should have null as their left child. And
you're making this a little more complicated than it is. Don't take out the details. I don't give a shit about the details. Describe to me in general. General plain English. Okay. High level.
Yeah. So essentially, like if we're given like any node, right? And all of their subtree, basically, we want to rearrange them in. We just want to rearrange them in pre-order fashion.
Okay.
Is that Okay.
So then how does that, you want to rearrange them in pre-order fashion. So then where does the recursive function come in then?
When we're traversing the tree.
Okay, so let's take this very simply. So in general, you're going to call like node 1, right? And then so you want to call function, let's say you call function on 2 and then function on 5. Let's suppose I gave you these pieces. Give me the algorithm. I think you're overcomplicating this.
Function on 2 and then function on 5?
Yeah.
Okay.
Suppose I gave you that. What do you want to do now?
Yeah, so I want to return, the output should be like a flattened list, but in terms of the algorithm, move subtree right. Oh, on the left. Right?
Okay.
Yeah, and then for 5, it would just be like stay the same.
Where is 5 going to be put then?
Oh, where's 5 going to be put? Oh, 5 is going to be put under 2 subtree.
When you say subtree, do you mean 2, 3, 4?
Oh, flattened list.
Yes, be very, very atomic about this. I really wanted you to stay that detail.
Yes.
Okay. So now that you know you need to put under 2's flattened list, how are you planning on getting there?
So I think was my like kind of idea with the pre-order traversal. Like I was thinking like, depending, because I know with pre-order, right, it's going to or I know with the flattened list, it has that pre-order order,
Mm-hmm.
right? So by traversing the tree in a pre-order fashion, I wanted to essentially like set each node's
Mm-hmm.
like children to the right.
Okay, good, sure.
Yeah.
So you would basically, yeah. So that input function, that recursion function, would flatten the subtree. I want you to be really atomic about that as well. Okay, fair.
Flatten
And
the subtree.
Yeah, flatten the subtree to a linked list. This is essentially what you're describing.
Yeah.
Okay, fair.
And so,
What?
you know, I guess because of the example, like, you know, the right subtree, there's not like too much to I guess like think about in terms of the flattening. So that's what I was concentrating, right? But like essentially it's just like when we're going through the recursive function, right, at node, like we say like nodes like node dot like right would just be equal to node dot left.
Sure. That's you writing the actual code, right? Though. I don't actually see like what exactly. I'm trying to do this without giving you the answer. Actually, it's kind of hard. So let's say I gave you. So I know you're doing node dot right equals to node dot left, but then how are you gonna move the tree to what's it called, the set under two's flattened list? I'm curious. Actually, how about this? Write the code, and then I actually want you to do that just so I can pick it apart later. But I think it might be easier for me to illustrate it once you do that.
Okay.
Or if you want to do this, if you still like can do the pseudocode for it, but
yeah, for sure. I guess I can just write the code.
If you feel a little bit more comfortable with that, but.
So yeah, like whatever like node dot right is, we want to set it to like node dot left. And so for this example, it's like 2 and then 3, and then for like node dot we don't want to like lose what like node dot right was, so I'll just set it into like a temporary variable. And what this would do is like we would continue on to oh fuck, never mind, I'm blinking. Node dot right. It's now node dot left, so 3, and then 4 is in this variable called temp. And so node dot right is equal to temp. Something like that. Yeah.
Are you sure?
Okay, so that works for like 2, 3, 4, but let's say like 1, like 1, 2.
Mm-hmm.
So 1, 2, 3, 4. And temp equals to node dot right, which is 5. Node dot right equals node dot left, which is 2. And then node dot right dot right. No, because it's not like calling it like recursively right now.
No, that's not the problem. What's the problem? It's not, I think don't get caught up on the technicals. Don't get caught up on the details. This is what happened last time. What is the biggest idea that you're missing here? What's the thing that you're failing to execute on? I'll give you 30 seconds, then I'll tell you.
Okay.
Because you literally just told me, by the way.
The thing that I'm missing. No dot right, no dot left. Yeah, I think I have to call this one.
Okay. You literally told me you're going to add the node to the end of the list, right? To the end of node 2's nodes 2 list, right?
Yeah.
Are you doing that here?
No, I'm not doing that there.
Okay, great. Yeah. So that's the problem, isn't it?
Oh yeah, yeah.
So then so then the question boils down to, how do I do that?
I guess like as long as we have like node 2's flattened list, right?
Mm-hmm.
Like if we keep track of like whatever the tail is
Mm-hmm.
for 2,
Mm-hmm.
we could just set like the tail, whatever, and the tail is being like the last one in the linked list.
Mm-hmm.
That dot right to 5, the head of 5 essentially, right?
Yeah, that's it.
Okay.
I mean, another option would have been, hey, iterate through all of through the list, because like you said, the function here would have flattened the list, and then you could just iterate over. But now your output has to be the tail end of the flattened list.
I see.
Like, you saw how the logic works?
I did, yeah. I think I was just getting confused between like what function 2 and function 5. Like I didn't think they were like the same thing, or I thought they were like the same thing. Yeah.
They are the same thing.
Oh, okay.
Like this, I literally told you function 2, function 5. What are they doing? You're passing in the node, you're flattening the subtree, and then the output will be what you want it to be, right?
Right.
So you already had this here. Did you ignore it?
I think so. Yeah. I did ignore it. Yeah.
Yeah. Why are you ignoring your own ideas?
I got kind of caught up in like the rearrangement stuff, I think. Yeah.
Okay. So basically, okay. So I guess in the interest of time, I will show you how to think about this, and maybe it'll be a little bit clearer. But but right now, this is not a good sign. It still feels like you're struggling with recursion a lot. So let's describe this. So, the bottom line is that we need a recursive function that we're passing in a node, we're getting out something, right? And recursive, all it means is a function that calls itself. So remember what I think I showed you the diagram of like me blocking off a chunk of the tree, right?
Let me look back in the doc.
If I didn't, let me go ahead and do that for you. If my iPad is charged, that is. Hold on. Yeah, give me a sec. Let me find my iPad.
Okay. No, I don't think you did.
Ah, damn it! It's not charged. Okay, so let me go ahead and charge it for a little bit, and then I will see if I can get the little tool going. Okay. So, basically, the bottom line is recursion. All recursion is a function, fundamentally, right? So, if I gave you a function that I promised where you give me a node, I will flatten that. I'll flatten it and give you the tail end of that flattened list, right? Let's say I gave you like let's call this like function 1. Function 1. You know, let's call it recurse. Right? And versus if I called like flatten. Let's call this like some black box function. You know, and let's say it doesn't do it recursively. So this is the not recursive function. The point here I'm trying to make is that if for every single input you got the same output, recurse and flatten would not be different. Does that make sense?
Recurse and flatten would not be different. Repeat that one more time.
If for every single input, if for every single input, recurse and flatten returned the exact same output, there is no difference here, right?
Fair, yeah.
So if I said, hey, let's suppose that I gave you a magic function that handled it for you. Flatten 2, flatten 5. This would literally just return the tail of left, right?
Yes.
And this return tail of right. So all that would happen after that is, okay, well, we need to move the left node to the right, move the right node to the bottom of the tail of left.
Right. Yeah.
Right. So what I would do is I just assign it to temp 1. So like prior left, equals to node.left, and then prior right equals node.right. And then I just like null out the nodes just for the sake of simplicity. And then just so I'm not dealing with like all these random ass variables that you got going here. So then node.right, move the left node to the right, right? So then we just node.right would be prior right. Well, I say prior left, right?
Mhm.
And then tail of left dot right would equal to prior right, right?
Right.
And right now I'm describing this recursive function, right? But because based on the definition, now that I've flattened this, now I need a promise that I'm going to return the tail end of the flattened list. I've made this promise. I've made this contract. So in order for me to make this whole, I need to say like, what's it called? It's going to need to return a tail of right, essentially. Now you see how I logically put it together?
Yeah.
And now the beauty of this is,
because right now you're
and then of course you can deal with like the null cases after that. But right now this is like the high level.
Yeah.
Does this now make sense?
No. Yeah, no, this makes sense. This almost reminds me of like symmetric trees or like subtree symmetric, because essentially what
I don't want you to think about this in terms like, oh, there's another problem that I saw. I want you to think about this term in terms of how to actually approach the problem. Recursive problems, namely.
Okay.
Like, I want you to imagine that for recursive functions, imagine I substituted the call to recursion with some other function that is like, hey, it's a black box. It doesn't matter. I'm going to handle this for you. As long as you've defined the contract.
I see. So in this situation, right, like we have two functions right now, recurse and flatten.
Sure.
Right. And flatten is not the recursive function, but it does the same thing as what the recursive function like is supposed to do. It's like flattening it out, right?
Correct.
And right now you're using it here within could I say this is kind of like the recursive function itself?
Yeah, you're defining a stage of the recursive function. And remember how I mentioned last time, like it's all about states? If you can handle every single possible state that gets passed in here, and then every single possible output of these left and right, you've solved the recursive function. And then you're free to make this flatten,
like
back to recurse.
So yeah, essentially like this is the recursive function that we define, like whatever it is, and like kind of in accordance to the contract. But instead of like actually calling the recursive function, right, you're just saying like, all right, let's just call this recursive function like flatten. Like let's forget that it's like we're recursing stuff like that. Like what is it to do? And once like we kind of establish like that logic, right? Once we go like, okay, hey, like it does what it's supposed to like kind of like do, then it's like we replace it with the recurse. So essentially you're just trying to illustrate the idea of like putting like the recursive function into like a black box, and then okay.
Yeah. So does this help you visualize recursion better?
I think the issue isn't necessarily like recursion per se for this problem. It was honestly just like how to rearrange the nodes in my head.
Don't do it in your head, man.
Because like it's like it's not like, oh, like, because when you say like the reason why I kind of brought up like the symmetric tree is just like, okay, yeah, I know it's supposed to be like, once we go down from each tree and stuff like that, we're splitting it off and so on and so forth. Like that in a sense can also be taken as like recursion, right, and whatnot. But I think it was just like the restructuring of it that like kind of was tripping me up.
Recursion is just a technique. I think you're still thinking in terms of details. I'm trying to break that from you. So let's go through the story, right? So we started off with, iterate through the nodes in a pre-order traversal, store the nodes in a array, and then join all the nodes in the array, right? Inefficiency. See, iterating twice using a extra memory, right? So how do we solve this? We solve this by joining while iterating, right? So the question is, what does our recursive function need to do? So our input will be a node, and then we need this to flatten. We need this to flatten, right? But then what's our output? Let's say for the instance, I don't know. And then you were trying like this example here, right? So you realized that, hey, I need to put the left child on the right hand side. I need to put that right child from before on the bottom of the flattened list of of the left child. You need to make this point very clear.
Mm-hmm.
And what you ended up doing was you didn't actually. I don't think you made that idea clear to me, and I want you to like essentially write it out like this, because otherwise you wouldn't have ended up in this like crappy situation of like no dot right. And I was like, because you didn't have that clear idea, you ended up like writing this. This is a symptom of you not having this idea. Does this make sense? Either that or you focus too much on the...
I skipped the ideation portion of like, okay. I think perhaps for recursion, like something I need to start doing is like, what does the function, and you actually touched upon this. Yeah, it's like, what's the input? What do I want to see the output be? Mm-hmm. And maybe thinking about what the output is like, okay, like I need to put the lecture on this. Okay. Yeah, I was doing that in code. And then I need to put the right child from before on the bottom of the flattened list of the right child. Mm-hmm. Yeah, I definitely remember saying that, but I didn't like, I think, write it out into the idea. So
yeah, I think it's the same problem from before. You're like talking about the idea, but you're not actually committing to it. I want you to write out the damn idea very simply before you write code. And I want to see this on every single homework that you do. I really want you to do this.
Okay.
And then that way you don't get caught in the situation and you end up doing things in your head. Okay. If you commit it to paper, it's like, oh yeah, this is why I'm on this path. You know?
Gotcha.
And then now that you know this, it's like, okay, well, let's finish this logic, right? So it's like, okay, so then let's say if my recursive function returns back the head of the list, then I iterate through the list, you know? But then in efficiency, I'm iterating, you know? Can I just return the end of the list instead and skip the iteration? You know? And that's exactly what we did. We just like changed the definition of the recursive function and changed our state, and then boom. Now we have our algorithm. So going through this logic and and finally acknowledging that this is basically where the crux of the issue is and why you kind of got stuck doing things in your head. I really, really need you to do this. Like, I'm not fucking kidding. I need you to take the idea of like writing ideas out very seriously.
Got you.
Yeah. Don't get hung up on the ideas. I'm pretty sure I've mentioned this before. Like, write out the ideas. Walk through ideas before you commit. Yeah. It's like walk through your idea. I keep saying walk through your idea. But then now it's like, okay, now I need you to write it out. So draw that shit out. Yeah.
Okay.
Write the idea very simply. Write and try it out. Write the damn idea. Very simply draw it out and run through it. Yeah. So I don't want to repeat myself again. If I have to say this again, it's not gonna be good.
Okay.
Yeah. So then with that, does this help you understand recursion a little bit better? And do you think you can execute on this?
Yeah. Let's try it. Let's try it out.
I'm gonna give you a problem then.
Okay. Can I use the restroom real fast?
Yeah. Go ahead. I'm gonna go get some water then.
Okay.
back?
Yeah.
Great. I'm going to go pull up a problem for you, and I really want you to practice this idea of writing out the idea and this idea of like looking at recursion in this particular way. Does it make sense?
Yeah. Yeah, no, I think definitely like I need to do like kind of what you like did, like what are we passing in, what are we getting out and stuff like that. So
Yeah, make that contract and then make sure to fulfill that contract.
Okay.
And I also want you to do this on all your homework. Yeah, all the problems that you do, walk through the idea simply as possible, and I want to see you do that exercise of pseudocode as well. And getting out all your ideas. Walk through the idea simply as possible. High level pseudo code. I want to see this on every single problem you do. Okay, clear?
Yeah, I think yeah. Okay.
Have you not been doing that, or?
No, I haven't.
Okay, I'm gonna next time. I'm gonna check on Thursday, man.
Okay.
Oh, speaking of which, is Thursday too soon for you for the replay? If not, I can push it back to Friday.
Yeah, could we do Friday actually?
Okay, I'll reschedule that on the Google Calendar after. So.
Okay.
Google replay. Let me go ahead and open up the. I already gave you the serialized, deserialized, and inherit tree, right?
Yeah.
Okay, good. Have you done validated binary search tree?
I kind of know the like the hack for that. So
okay,
yes.
then never mind.
Yeah.
How about implementing a iterator for a binary search tree? Have you done that one?
No, implement an iterator. No, I haven't.
I mean, this one might be a little bit. No, actually, this one's a little bit too hard for you, and it's not really what's it called suited for recursion. Actually, let me give you a different problem. This would be a different. This is gonna be a problem I'll probably give you next week if you do well on the recursion stuff.
Okay.
Have we done kth smallest node in a binary search tree?
No.
Okay, then let's do that one. This one's a good one. So find the kth smallest element in a binary search tree, and I really want you to focus on this idea of walking through the idea, writing the idea out on paper.
Okay.
Write the idea out on paper before you write code, as simply as possible. We're not doing shit in our head. Everything goes on paper.
Okay. Okay. So, find the kth smallest element in a binary search tree. So we have the kth smallest, like second smallest. It would be like the first smallest would be 8, the second smallest would be 12. Yeah. This would be much simpler to do if I could like order these somehow.
So like do them in order? What do you mean?
So like if they were like sorted, you know, so if they were like sorted from like let's say we had like K, if we have the second smallest, right, then 8 would be like first.
Yeah, the second smallest, so yeah. If I told you the first smallest, I want you to give me 8. If I give you second smallest, it's gonna be 10, right?
Oh yeah, second smallest would be 10. Yeah. So yeah. Oh my god. So yeah, it would be much simpler. Oh, let me think. Oh, since it's a binary search tree, if I just recursed, no, stop thinking about just recursing now. If I just traverse this tree, and if I just did this, in order is root left, be left root. So like, I think the idea is like, what if we traverse the tree in some fashion such that it is, you know, in from like least to greatest, right? Because this is a binary search tree. And so like, if we were to do, let's say, in order is basically, we would do left subtree, visit root, and then right subtree. And I also know that like for in order, if like the in order reversal should return the nodes, for lack of a better term, like in order, right? So if I just keep track what node I am on, then on the eighth like node,
Okay.
I could just return that.
Okay.
Yeah.
Well, what? Okay, keep track of what node you're on, and then on the kids. Okay. Sure.
Yeah. So let's see. So this is just my this would, I guess, would this count as my idea? Right.
I mean, it seems like you, and I want you to walk through an example. Like you wrote out the idea on paper. Great. I like this. Now I want you to walk through an example just to make sure you understand it before you commit yourself to code.
Okay. Yeah, sure. So let's do input is or should I start writing the input out and stuff like that, or just
If
like
you if you think you need to define the recursive function immediately and it helps, then go right on ahead.
let's do that. Input is like node, and the output is like node like value, right? And
Wait, why do you want to return the node dot value in that function? What are you promising and how are you using it?
um okay, let me just say I don't know what the output is yet. Okay, let me think. So we pass in a node, traverse the left subtree. So um like leaf. Oh, the output would be like node value, because like once we find the kth, like once we find the kth smallest, we want to return that value. And the recursion. Yeah. Without like.
Okay, input node pass in. Okay, so you're gonna pass in the node, sure, and you're gonna traverse. You want to traverse the left subtree until you hit a leaf, and then the
like
output.
Traverse the tree in an in order fashion.
Okay, so you're gonna traverse the left subtree in order fashion. Okay, or whatever node you're in, and then the output of that is the node value once we find the kth smallest, we want to return that value. Okay. So then if you find the kth smallest in that node's or that node's subtree, you're going to return that node, right? Is that what you're saying?
Yeah.
Okay. So instead of saying, I guess because okay. So what happens if you don't find it?
If we don't find it, like we would just return, right? We would because we're doing the traversal. Yeah, if we were just to return, like else we would return and continue traversing.
Return what?
Return we would just return we could either just return nothing or we can return none. Yeah.
Okay. I personally would say instead of returning node value, because these values might be repeated, I would just return the node.
Okay.
And then null.
Yeah.
Okay, fair. All right.
Okay.
You define the contract. Let's see if it's the right contract. Go ahead, keep going.
Okay. So let's say we pass in this node 15, right? So function, let's just say 15. And we're testing it right now. So we pass the node and we traverse the tree in an in-order fashion. So now we want to do we call it on the left the left child. So left child function would be 10. And we do that again. Is like 8. And we see here that essentially it's like a leaf node. And kind of going back to the like idea, like we want to be keeping track of like what node I am on. So let's see, like how can I, now that I know this is like the leaf, we go back up. Right now I'm just trying to think about like how can I keep track of like what like the K, like what number out of the total nodes am I on? So if like, let's say we were also passing in shoot, I'm stuck. Let me think.
Okay.
Nice.
So what do you what do you need to pass in, and how are you going to determine the K? Node?
Yeah. So originally we were just passing the node, which made sense because we're traversing the tree. But right now we also need to keep track of like, okay, like when does the K counter like start, right? This is going to use up like extra space, but like I guess for the sake of like it being like naive, I'll just
you can start with a naive solution if you really want to, but then yeah.
Okay, so like we know that for in order fashion we're going to go this way, right? So we're at this function 8, and obviously like once we go into the children of 8, we find that's none, and then like we would like start returning, and then we would actually visit what 8 is, right? So now we're at visit 8, and what we can do at like for every time we like visit a node, we increment a global K, global counter.
Sure.
Let's say. So like, and how we choose to do this visit is like, where the naive part could come in is like, you can either append it or like once it returns, like whatever the case might be, like every time we do that, we increment the global counter, right? So visit 8, and this leads to counter plus equals to like 1. The counter now equals to 1. All right. And so, okay, now we traverse the tree in an in-order fashion. So we did this part, the K gets updated. And now the output would be, is the node value like, it's not, because it's not the K smallest.
Okay.
So we would return none or null, right?
Okay.
So this would get returned. This returns, let's just say.
Okay, what your counter is 1. Sure, you mark that. Great. Function returns none. Cool.
And then again, like, you know, since we're in the recursive kind of part of here, we're still like in here, right?
Okay.
So now we visit 10. And 10, you know, allows us to bring our counter up to 2. Okay. And now we're returning from 10, right? We're returning from 10. Yeah. Wait. We visit 10. And actually we're about to go into like the right subtree.
Okay.
So like we want to, but then like the thing is we want to return like the smallest K, and since we already found that, we want to return that value.
Wait, your K is, what value is your K right now?
The K is let's just say it's 2.
Okay, sure, your K is 2, right?
Yeah, K is 2.
So then what do you need to evaluate?
And so right now we need to evaluate like, okay, once we find the K smallest, we want to return that value and just like end the recursion. So we just want to do like return node 10.
Okay, let's put a pause here. Now that you have this idea, what do you need to do?
Now that I have this idea, this was already kind of like testing it, right? So now I'd go into like the pseudocode.
Why not add it here?
Oh.
I mean, we talked about writing the idea. I was like, and it wasn't clear to you before, so maybe you want to do the compare. You say if you're on the kth node, maybe add that little detail here. If you're not, it's like if you kind of struggled on the detail on that, maybe write it out.
Wait, I'm sorry. Why do I need to write it out again?
Just say, hey, like if my, because you were struggling to say, oh, I just need to make sure my counter equals to K, then return. Return the node. You were legitimately struggling to just even express that idea.
Oh, I thought I expressed it like here.
I mean, okay, but then it's like I sense a lot of hesitation when you were developing this step.
Okay.
So it's like that's where I was like wary, like, oh well, you need to return. So that's part I was like, are you sure that's clear in your head?
Okay. No, that's fair.
Yeah, it's like if you have that hesitation, I want to like if that hesitation, let me write that down. If you have that hesitation while executing on your pseudocode, code or idea, probably write it out. So that's like why I would say, hey, maybe you want to do that. So.
Okay. Yeah, makes sense. So yeah, keep track of what node I'm on. Then on the K node, I could just return that. I could just have this more defined. Return that node and recursion.
Uh-huh.
Yeah. I'll just underline this. Yeah. Okay. Yeah, I think my idea is like sound after kind of like testing it.
Okay.
I could run it with like another example, but I think in a sense this is the pseudocode, right? So I can start coding, I think. Yeah. So I say function node, input is node, pass in the node, traverse tree in an in-order fashion. So before the function, let's just say we have something called counter, right? And it's going to be a global variable, and we can always keep track of that. And we know what our K is. Let's just say K in this situation, or it doesn't really matter, right? Like, because k is something that we get, and this can just be defined as like, let's say like a helper function, right? Or something. So we have what it kind of says right here. Shit, I need to organize this better actually. So that's not true. Okay, so this is the contract that I'm giving it, but this is actually what my pseudocode is. Yeah, keep track of the node I'm on. Oh, I can flush this out a little more. Keep track of what node I am on. Increment counter every visit.
Okay.
And then on the kth node, I'm just going to put this aka counter equals k. That node recursion. Okay. Yeah, this is just detail. This is the actual front of it. Okay. We have the contract input node, and this is just me being finicky with details, but we just want to do top left. Function node.left. Then we can just do like if node.value, and this is like the equivalent of visiting something.
Okay.
Just not do anything with it. If node.value counter plus equals to 1, and function node.right.
Okay.
And in the visitation.
Wait, what do you mean if node dot value? I don't understand this. Why are you checking if the node has a value?
Well, this is more just kind of like keeping in context with the in order traversal part. It's like on every,
do you need this if statement? Do you need this if statement though? Let me ask that.
No.
Okay.
Yeah. So I can just get rid of that.
Okay.
Plus equals to 1, and then if counter is equals to k node, and we're calling function dot right. Okay, now here's the part, right? This is, you know, where I need to make sure my contract is there. Return that value on the recursion. I guess once it starts returning like this, it will return node.right. Counter equals to k return node goes up. Yeah, I think this is about does it.
You sure? Are you sure? What does your function contract say?
The function contract says input is node and the output is node value.
What does that node value mean?
Could be node.value.
What does node value represent? Let me ask you that.
The node value represents the kth smallest node.
Okay. So, which means...
Which means that I need to be returning... Well, once the counter hits k, we want to be returning the node, right?
Right. And yeah, sure. But what else does it mean?
We can end the recursion.
Sure, yes, but let me make this more clear. What happens if your function node.left, this line, returns a node? What do you want to do?
Oh, we want to return that. Right. Oh, if it returns a node, then that means we found it in that left subtree.
Mm-hmm.
And we don't have to like do all of this.
Mm-hmm. Which means that you need to. You need to.
If it does that, then
Just write it, man. It's okay. Just write the code.
okay.
You know the answer.
Oh, just like return.
Return what?
Return whatever the function returns actually, because the function is returning a node value.
Mm-hmm.
So if we just say left subtree, return left subtree, and we want to go through all of this stuff.
Mm-hmm.
Yeah, and let me see real quick if we do the same thing for this. Otherwise, we return none. Yeah.
Mm-hmm.
I think so, yeah.
And
Yeah.
you're missing one more thing. You have a little error here. Where's your error?
Oh, return. Yeah.
Sure.
Yeah.
Okay. How difficult was that?
Not too difficult. I think I got careless towards the end because like I wasn't I had like I think the basic part down, right? But essentially when it came down to like and I think like I kind of knew this when I was like, oh, what do I return here? It's like I knew that it was like, oh, if I return nothing, sure, kind of stuff. But in reality, it was return none with the contract. So yeah, I didn't account for the kind of like the state kind of stuff you were mentioning. So like if the left subtree finds something, like we don't have to be doing all of this stuff right here, you know, and so on and so forth. But I think like in terms of the basic idea, I got it though.
Yeah, like this is like I set you up for everything. Like you walked through the code, you knew what to do. Your stack trace showed you knew what to do, and like you had the idea down. And then if you still kind of fuck this last part up, I don't know. Like I'm trying to figure out like how you don't make that mistake. I'm trying to figure that out.
Oh, so it was this part that I fucked up, right?
Yeah, it was literally this part. Like, hey, what happens if it's you know, you found it in the left subtree?
Yeah, fuck. Yeah.
I mean, like you literally wrote it down. It's like you made the promise that hey, if I found it in the small in the function, it's like it's gonna give it to you, and I'm trying to figure out like how I can prevent you from making this mistake.
I think I was thinking, for lack of a better term, I think I was just thinking 1D, like low key,
Okay.
or like 2D, because it was just like, oh, as long as I find like the counter, then we just return that. But I wasn't considering like the 3D scenario where it's like, let's say it wasn't at like that iteration we found it.
Right.
And it's just like a small kind of jump over, right? It's not like a huge logical leap.
It's really not. Yeah.
Yeah. Because it's like I'm calling this function. I think I was relying on just kind of like, I think this might have just been like low-key a syntax. I want to say it's a syntax thing because it's like I should have known that like, okay, we call this function, but this thing is returning, right, like a node. And like we need to be setting that to something. Otherwise it's kind of like pointless. Like what if we return like none right here, we return nothing, like that was kind of like, I should have kind of thought about it like right here at this part, because when I was returning from this, I should be thinking like, oh, was it if it returns none, or if it returned like something like a node, like I should be returning that. So
Yeah, basically what I'm seeing right now is that you you tunnel visioned on this like the node you're at, but then you need to that the whole point of recursion is that I'm gonna be able to process shit, don't care what's going on down there, and then coming back, and then I need to be able to use that in some meaningful way. So,
okay,
when you're doing recursion, you are processing things in subtrees. Don't ignore those results. How do those results play into your bigger algorithm?
got you.
Okay. But overall, doing this problem and like really writing down the idea, did you feel better or worse about it?
Oh, I feel much better. I mean, like, yeah, I felt much better actually.
Uh-huh.
I don't know if you can tell in my voice. I was like just really calm, kind of going through this. I was just like,
I did hearing you were stressed.
oh, never mind then. Yeah, sure.
I mean, yeah, if you're calm about it, but you need it. It's like I need you to be faster. Like a lot of this like stuff is just like pure like just a step in logic, really. Like every single time, like I say, but this means, all it really is just one more step from that logic. I think that once you kind of recognize that, I think you'll be a lot faster at it. But it's like literally just asking yourself, what is the next logical step? It's like Sherlock Holmes, it's just like deduction. It's like, hey, I've already written this idea. It's not like some crazy ass leap in like no magic bullets exist. Just consider that. And everything else that you've done up here is like you've already acknowledged it, right? Like the kth element, the kth node, the traversal. So then all that's really left is like, oh well, what? It's like if I know that I might find the kth node in the left subtree, it just means I should probably return the result of that in my actual function. That's it. Because my contract for function says, hey, I'm going to promise you that, like you wrote this down. I promise you that this function will return the kth smallest if I find it. So if I found it in the left subtree, why don't I just use that?
Right.
So
yeah, I think the contract helps. Would you say I'm getting better at recursion? I don't know. Like
a little bit better, step by step. These things don't take are gonna take a while, but right now I'm getting you better at recursion by trying to make you do things that are, agnostic to every single problem. So that way we're not like focusing only on recursion. We're hitting every single problem in theory at the exact same time just by working on fundamentals. Because from what I see, you're fundamentally lacking in logic. And so what I'm trying to do is really enforce all those exercises like do the pseudocode, write out your idea, because I still see you're trying to do things in your head, and that's really like tripping you up. If I can get that out of you, and then give you like maybe and make you work on it for like 40-60 hours a week for like 2 weeks, then I think we can make a lot of progress. But right now, the thing I see here is that it kind of boils down to the kind of very similar mistakes where you have this idea in your head, but you get like hung up on them sometimes, or you like, other times you just like straight up ignore it altogether. I'm trying to get you to write it out. That way you're forced to acknowledge it on paper.
Okay. Yeah, I'll try that approach this time. Yeah. Okay.
It's kind of like the same problem from like the past 3 weeks. But like this is gonna take time. But I'm really hoping that this week is like a week you get over that, and then recursion will then start clicking with you.
Okay.
Yeah.
Gotcha. Okay.
So we have 20 minutes left. We can. It's not really enough time to do problem. We can go over your schedule and let you go early, or we can try do it. Let's do your schedule, and then we'll save the last few minutes for questions if you have it, because I'm pretty sure you're gonna have some.
Sure.
Okay, so DFS. How much of DFS and subsets have you done, by the way?
I finished all of DFS, like subsets. I like got the pattern pretty much. It took a while. But I guess for subsets, I only have 1 or 2 from Brocking left. Yeah, that's pretty much that's pretty much it for like subsets. Yeah.
Okay, I want you to redo the DFS stuff that you failed or you did or took too long. So I want you to do that. On the problems that you didn't like do well on, I want you to redo it, except use this approach. Because to me, like even though you're done with recursion and DFS, you still really suck at it. I'm not gonna lie. Because like so to me, I'm like wondering, what did you spend your time focusing on? Why is it like not where it's at? So I'm gonna say redo the DFS stuff. I'll take a look at it on Friday. Now, have you done EPI DFS, or are you still working on that?
Yeah, I have. I think instead of doing the depth first search from Grok, and can I just do the the ones that I like missed, like sure I'll do them, but I kind of think like doing the legal problems also is like pretty helpful as well.
Do the EPI ones because I really want because EPI if possible
Okay.
because the reason why is like you'll get a lot better signal with that. I think
Okay.
to me Grok like lead code is just a spot check. Lead code should never be used as a oh yeah I need to practice it because the reason why like you saw earlier that it accepted a suboptimal solution in theory, you know. So
Yeah.
it's like if you're with EPI, you're forced to consider things that you don't generally consider. So I really want you to focus on the EPI. I know like they give you a schedule of like, oh yeah, do these this problems. I want you to do every single problem.
Okay. Every single problem. Okay.
Yeah. Every single problem if you need to. So I want you to focus on EPI that on that part. Now let me look at the book. Give me a second. Okay. Let me look at the chapters. Language design question, domain specific, parallel computing graphs, blah blah blah. Okay, so you did all of the recursion chapters, correct? Or
No, actually no.
okay, so I want you to do those. Binary search tree as well. Yep. Have you done chapter 15?
Me take a quick look.
Sorry, the binary search trees chapter.
Binary search tree chapter. Is that the trees chapter?
There is a there's binary trees and then there's binary search trees.
Okay, no, I haven't.
You done binary trees?
Yeah, binary trees.
Okay. I want you to do all the problems from binary search tree and binary trees that you didn't do or you did poorly on. And I want you to practice like all the stuff that we talked about.
Okay.
I still think that this is like, if you can get over this, I think the rest of the stuff will come pretty easily. But it all depends on. I think we might be able to barely make 10-14. Yeah, it depends. I think a lot of it's gonna boil down to how hard you work this week.
Okay.
And if you can nail this down. Like if not, if you can't nail it by next week, then we're gonna have some problems.
Shit. Okay. Fuck. All right.
Yeah. If you can get like 80-90% of the way there in 1 week, I'll be very. I think that's what we need to target. Like, I mean, I definitely there's a lot of things I could have done as well, but like I need you to like try this, like really focus on it, like take it super seriously.
Okay.
Gotcha. Okay, now have you been keeping up with like the schedule? Like, has there been any disruptions in like because October 30th you said you're out for the majority of the day due to Halloween. Any other disruptions in the schedule?
No, to be quite honest with you, like maybe like on certain days it would be 2 hours instead of like 1 hour. But for the most part, it's been pretty consistent. I think like the progress in terms of amount of problems I'm churning out has slowed. But I think that has just been two things really. It's one, the subsets one is like a pattern that I'm not familiar with.
That's fine.
And then two, it's like with EPI, it takes much longer to kind of like do and whatnot. So
that's fine. I don't care about the number of problems. I care about the quality practice.
Yeah.
And I want you to always look back at your own thinking, like, oh, I could have done this faster. I could have skipped this step because of this observation. I really want you to like really critique your own thinking. You know how I saw all the details of like, oh, this might fuck you up. This area might fuck you up if I went this route. I want you to be able to do that to yourself. Be really super critical. Don't like say, oh, I could have done this better and whatever. It's like, what happens if I tried this path? What happens if I tried this path? Be really thorough in the critique.
Okay. Just out of curiosity, like let's say like you or me, right, and stuff like that, and like you're doing this problem, like when would you fit in like kind of like the review aspect of it, like on like just kind of like a week basis?
I would do it after every single problem. Even when I was doing these problems, like I would literally just like if I didn't get the problem or I got the problem, I'd literally just like once I'm done, like maybe take 5 minutes to use the bathroom or some shit, and then look at the problem, look at the step by step I took through my logic. And then say, oh yeah, this area I took a little too much time on. Why did I take too much time on it? And I just like reverse engineers. Like I did this because I assumed this, and I did this, or like okay, and then eventually you arrive back. Why did I make that move? Why did I write this? What? And eventually you arrive at this one thing, this one little move that you made that kind of fucked it up. And in this case, it's almost always like you didn't write down the idea. Like if you go back to like what we did today, a lot of it was when I did the whole like you have a lot of hesitation. When executing the pseudocode, why did I have that if I was looking back on it, I'd ask myself, why did I have that hesitation? Like, I knew it, I wrote it down, or wait, oh, I didn't really write that down because I was doing the counter thing. I have that hesitation. Maybe I should write it down, because then I can just copy paste or like just go by what I did in the pseudocode. Or if the pseudocode, it doesn't contain. Another way to read it is that the pseudocode or the idea that I wrote down didn't have enough information on it. It's like, do I need to add a little bit more information? If so, what information do I need to add?
Okay. I think I need to implement that actually as well, because it's like I'm doing a lot of these problems, but it's like, yeah, the review. Okay.
It's a review. Like, I really need to do the review very seriously. Like, my curiosity, how have you been doing the reviews before?
Honestly, it's before like the replays.
Okay.
So like I'll pick maybe like a question that I think, because I used to just do them all, right? Like I would like film myself and stuff like that, but then the replay would just like happen on Thursdays. So then Thursday would just be dedicated to me like going through like 1 to 2 videos, and like doing that kind of critique.
Okay. I want you to do the critique on every single problem.
Okay.
Like I don't know if did I write that before. Let's see. Let me see if how many times analysis. Replay. Do the replay as if you're talking to interviewer. Let's go to replay. Do the replay. Okay. Yeah. That explains actually kind of a lot more now. You're doing you're doing it, but it's like it's not the reason why it's not the progress I expect, because you're not doing it on every single problem. I want you to think about it on every single problem. So maybe I should have been more explicit about that.
Even the ones where it's like that I got.
Yes. Correct. Because there's like, oh, I could have been faster at this. I could have done this better.
Okay. And for the replay, they don't have to be replays on like the videos, right? It can just be like, me doing the problem and thinking about it.
Yeah, in general, but the recording also helps because that way you can like scan through like, oh, I spent too much time on this.
Okay.
Personally, I always recorded myself, but I know people don't like that. So at the very least, understand where you took the most time, and at least target like the top 2 areas that you took the most time on, and then just like, what happened here? Why did I do this? But this is where recording really helps, because then like you kind of misremember things because you're always like focusing on the problem, but then recording might suggest something different. So it's like being honest with yourself, really.
Okay. Yeah. And I guess I have like a couple of questions regarding like, I know we're spending like, and rightfully so, on like the fundamentals and whatnot. Like, but I have like, some phone screens and also like online assessments due. Like, would you suggest that I just focus my concentration on kind of like our study plan and just kind of go into those, like, or would you say like I should try to do some problems on like the side maybe? I was thinking more so of the former, because it's just kind of like, all right, if I have like the logic down, then any problem they throw, I should be able to like do.
Well, you haven't gotten the logic down as far as I'm concerned today. So it's like, if I like, okay, let's say after today, after today's session in 10 minutes, if I said do an online assessment for Google, would you be okay?
No, but like my thing was just more so like prioritize getting the logic down, right? Like, yes. That's my kind of
get these good habits down, and then every problem will be easy.
Okay, got you.
Like, it's like we're looking for long-term investment on solving any problem, no matter what we're doing. We're not trying to play for short-term.
Okay, got you. Yeah. Okay, sounds good.
Yeah. So it's going to boil down to how seriously you take this replay, and problem solving and self-critique.
Okay. Yeah.
Okay. So then, read the DFS and binary search tree, and then how strong are you with dynamic programming? By the way, I just want to do a little bit of a heads up on that.
In terms of for DP, I kind of just memorize it, like, yeah.
I did not like that answer. Okay, and I know we haven't really focused too much on arrays yet. Okay, you know what? We're going to stick with this plan. Let's hit these recursion stuff hard, because I think once you get the fundamentals down, I want to show you how that applies to array after that.
Okay.
And then once you get that array down, then it's like, okay, well, now you see how they all merge together. Then we're ready for the phone screen.
Okay.
So these fundamentals are going to be super important. So yeah, I do the replay.
Okay. So for this week, it's just redo the DFS stuff that I took, that I failed too long, every single problem, and do the problems from binary search tree and binary trees, like chapter, correct?
Yeah. And how good are you with linked lists and hashes as well? Hash tables.
I'm sorry, say that again?
How good are you with linked lists?
Dude, I'm actually kind of bad at linked lists.
Fuck. Okay, we got a lot of problems then. Yeah. Okay. I think, okay, we got a lot of problems. This is not good. We might need to push back the target date. We're getting hung up on this because you didn't do the replay analysis. I should have been more clear on that. All right. So, okay, no problem. It's just 2 weeks in. We're addressing the issues. Okay, so let's do this. Tentatively schedule the phone dates for the 21st. I'm gonna say I am for like 1 week. But I need these next 2 weeks to be like literally your entire life. If a friend asks, oh, hey, let's hang out, you say, fuck no, I'm going to study, and I need to do everything that Edbert asked me to reach out on Discord if at any moment you feel like, shit, I did this 3-4 times, I'm still not getting it, what the fuck's going on? Yeah, I need these next 2 weeks to be like literally your life. You don't care about anything else, okay? Okay, cool. Yeah, and I know I'm being rough on you, but it's like we were trying to get you ready for 6 weeks. And it's like I thought we'd be like once we clear DFS, I thought, okay, well, you have some grasp on linked lists and arrays, and then we could do DFS after the phone screen. But I think we might need to hit that a little bit earlier. So yeah.
Okay.
So any other questions for me?
No, not really. I think I just need to not be afraid, be more confident in my thinking. And, yeah.
And you're gonna get confident by self-examining your own thinking and just like look at every single possible angle where you could have fucked up and how to protect yourself against that and how you can get faster and better.
Okay.
All right.
Sounds good, man.
Okay. Yeah. So I will go ahead and reschedule you for Friday.
Sounds good.
All right. Cool. All right. I'll let you go then.
All right. Bye. Have a good night.
Have a good night. Okay. So let's see. Hold up, give me a sec, guys. I am going to reschedule the, let's see, so let's do this at 9. Okay, and then after that, all right, let's see if you guys have any questions for the stream, I will be happy to answer them. Let's see what this stream, there we go. Wait, what? Warren Buffett's latest trades. Nope. Wrong window. Startup dinner and SF. Nope. Wrong window. Jeez, where the fuck is the window for this? Nope. Wrong window. Wrong window. Oh, there we go. Found it. Okay, so Juan asks, hi, is it useful to redo past problems? Honestly, I would say that if you didn't do really well on a past problem, I think it's worth redoing, and trying to figure out how you get faster and better at it. And it's like, you can theorize how you get faster and better at a problem, right? But you need to also make sure that your analysis is correct. Like, how do you know your self-evaluation is correct if you don't actually try it? So redoing past problems that you really sucked at or you failed at or didn't do well at, super useful. It's a validation of your critique, because you're gonna get the wrong ideas with self-critique. Nobody can actually do the self-evaluate 100% all the time. We have this idea, and I really hate this idea, in culture, where it's like, oh yeah, if I read enough and I think really hard enough, then I can invent the solution to everything. And the truth of the matter is that a lot of times we're wrong. I'm wrong a lot of the times, and I'm always trying to improve my thinking of and how I could have done things better. And these ideas are gonna be wrong, and so the only way to really know if we're right is to test it and make sure that we can get consistent results. So if I believe that one way to fix, say I have a problem in problem solving where I think I need to write more details, then I'm going to write more details on every single problem I do from now on. And I should see over time and across those problems that my hit rate, my success rate should improve, right? And if I know that the one variable that changed and I see that improvement, then I know that was the right idea. If I don't see that improvement or I see a decrease, then I know that's probably the wrong idea. Or maybe that there's something else at play, or it can get very fantastically complicated. And because of a lot of these interlocking and dependent problems, you can get a heck of a lot worse than get better. So that's why your mind's like, oh, well, I'm getting worse. Maybe let me something else. Let me try something else, Especially when it's interlocking problems. You just end up doing too many things wrong that it's really hard to self-judge. So this is where I come in. That being said, so going back to the original point, yes, redo past problems, make sure your ideas of improving or what you need to do are correct. So Crow says, hey, I'm antsy. Yes. I mean, I take a stake in my client's success. I don't get paid. I don't get paid for this unless he succeeds. And so really, I have a huge vested interest in making sure that he's doing the right things and following the schedule, And that's why you hear me always say, oh, maybe I should have been more explicit about this. Maybe I should have said this a little bit clearer. I should have done this. I should have done that. I can't put all the blame on him because, it's on me. I'm the one telling him what to do. And if he's not doing it, then that's on me because I may have said something wrong. I could have not been clear about something, and there's always a solution that involves me because it's me and him, he's trusting me to get him those results. And I, need to be able to get those results no matter what, for him. So I take a huge personal stake in it as well, not just like the financial stake as well. So, yeah. That's basically why I'm antsy about it. As you can see, I'm taking this really fucking seriously. So I hope he's taking it as seriously as I am, And that's why I say, message me at any time. I'm going to do everything I can for you in order to help you get this offer in this amount of time. So, Crow says, if I were interested in your services, what is the minimum knowledge that you would need to master before contracting you? I should not have to explain to you how a heap works. I should not have to explain to you how a hash map works. I should not explain to you how dynamic programming works. You should already have a basic understanding of this. Where you contact me is that, hey, I've put in a good, earnest effort. I've done a lot of leak code problems. I followed everything in your guide. I've tried grokking, I've tried API, and I've tried everything that I've seen and done in the guide and everything that you said. And that isn't enough. At that point, contact me for like long-term coaching. But if you're looking for a one-off session, that's like, hey, I need a spot check. What can I improve on? Then you can book me for like one of those one-off sessions. So to plug my website, go to eChanTech.com, look for the coaching services tab, and book me there. The minimum, I would say, in order for it to be worth your time, you need to have put in a good, solid effort. And you're a student, you're asking me as a student. I'm happy to offer you a discount if you ask. If you can't afford the coaching and you need some like discount on the services, I'll be happy to give it to you. I don't believe in taking money from people who are not like capable of getting results. That's just not me. And especially if you need help and you need that one little extra push, then I'm happy to do that for you. So, what is the magical number of leak codes is enough? There's no magic number. It's basically you need to have been burnt out by it. Like you have tried everything in the book. You've tried as many leak code problems as you can possibly fathom. You're out of ideas. You've tried everything. So it could be, 100 leak code problems. It could be 400 leak code problems. I don't know. It's like I need you to really have given it a good, honest, hard effort. That's what I ask. And I need to know that you're still capable of putting in that effort after we've done like a session or two together. That's my requirements. I'm really filtering for like qualified candidates here. So, yeah, that's my answer to that. Are there any other questions from the crowd, man? I'm open to whatever. You can ask me my questions about my career, other coaching services, how this client did, etc., etc. All right, going once, going twice, 3 times. All right, so I guess with no more questions, we're going to stop the stream for tonight. Thank you for watching, everybody. We will be streaming on Thursday night. We'll do the replay analysis with R, and then we'll do a Friday night replay analysis with K. Both of these will be at 9 p.m. Pacific Standard Time. In case you haven't noticed, I did set the stream visibility to be unlisted. I put those all in a playlist because turns out filling my video channel with streams kind of didn't really work for the algorithm. But if you guys want to find the past streams, they're all in a playlist. And I can message those to you, but just look under playlist, look for live streams. They're all going to be there. So with that, have a good night, and hopefully I get to see you guys later.